Welcome from my side as well. My name is Hendrik Heißelmann. I'm a scientific coordinator at SETWind, the Center for Wind Energy Research of the Universities Bremen, Hanover, and Oldenburg, and I'm located at the University of Oldenburg. Today I'm going to give a very brief overview of what we are doing in a project, in a German national funded project called WiSAbigdata, which is about a virtual wind farm site assistant for operation and maintenance decision support. So it's targeted at operators in the end. And what we are trying to do in this project is to use advanced methods from basic research, but also methods which are currently in wind energy, but are used for 10-minute data, and we want to advance those towards higher frequency data. So what is basically the research gap we're tackling? We all know, and we've heard that in the presentation by Sarah earlier, that of course there's quite a lot of data each wind turbine basically produces. That's on the one hand due to the ever increasing number of sensors which you can deploy in wind turbines. They're getting cheaper and cheaper, and it's way easier to connect those. So there's on the one hand there's more sensors in a wind turbine. There's more wind turbines, of course, and these turbines are getting even larger. So in the end we get more data. And then there's also more atmospheric data. I don't know. Can you see my pointer basically? The cursor of my mouse? Yeah. Anyways, so this is the one side of the data. This is usually some kind of structured data which is like electronically captured and stored away. And then on the other hand, we have some heterogeneous non-structured data, which is typically like the maintenance log. We have error codes, or we have status logs, and we have a lot of data which is, in some companies it's stored away on PDF, in others it's somehow in a database. It's quite heterogeneous, and is quite a challenge for data analytics in this way. And as I mentioned, what typically happens now is a lot of data is 10-minute data, at least what is stored away for a shorter time frame. You may have higher frequency data, but often 10-minute data is what you have available for long-term historic data. So in our project, we want to advance this by getting to the analysis of high-frequency operational data. We're talking about the order of 1 second data, maybe 2 or 3 second data. It depends a little bit on what kind of system you have in there, and then use this data to provide information for early fault detection and for the diagnostic of the state of your wind turbine or your wind farm. And by using this, we want to provide decision support for the operators to, on one hand, improve the planning of maintenance, and on the other hand, of course, improve the availability of your asset. And this aligns quite well with the wind energy digitalization task of the IEA, where you can see that there's, on the one hand, a work package on data science, and on the other hand, you can see these work packages on digital O&M, which have been combined with a work package for end-of-life assessment, which is basically closely connected to what the state of your turbine or your asset is. So our project consortium is quite diverse. We have a couple of partners from research in here. We at SETWind are joining with some other groups of the University of Oldenburg, which are dealing with basically oceanography and IT science. We have some basic physics groups in here, but also Fraunhofer IWIS, so it's also some wind-specific research here. Then we have some partners who are grounded basically, or who are basically coming from IT solutions, and some consultancies. And also, of course, we have some operators now consortium, because in the end we need the data, we need the domain experience, and this very diverse consortium makes it possible to tackle a challenge like what we're looking at. So what we are aiming at is taking basically novel methods which have been used in other fields, like for example financial analytics of financial data or traffic data, or like basic physical systems, and migrate those or adapt those towards the usage in wind energy data or in wind energy science. And then also we want to combine different methods to get an extra knowledge about that out of that. So once we have, for example, you can see in the sketch here, we have a work package on data-driven methods. So in this work package, basically all the methods are developed or further developed. We have a basically, once we evaluate these methods, we can select the best method for a certain problem. And as a backend for those, we have a software and hardware platform where we store the data away, and on the other hand, we run these methods. So that's basically not something you do on your personal computer or in your office. So there's a system behind that. And in order to not only do that from a research perspective, we have a work package which is dedicated to the decision-making processes of our industry partners and the optimization of the decision model, basically. And in the end, what we want to come up with is to take these methods or take some of the selected methods we have in this project and transfer those into a demonstrator software, which can be used by the operators in terms of a practical evaluation. So what we've heard already is that there's some challenges. On the one hand, we have this heterogeneous data. We have different sampling rates for different sensors. We have this is not only the sensor sampling rate, but it's also how data is pre-processed in that way. We have between different turbine types, between different wind farms or different operators, we have varying numbers of channels which are provided from the turbines. We have these status or error codes, which are also differing between different turbines. And if you're not only dealing with one turbine, that always is a challenge. And of course, there's this overarching challenge, which is about data availability. How do you get data for research projects? Especially high frequency data is often not really available, and service logs are also not widely available. That's something that somehow goes into the direction of what Sarah already mentioned, that you need to have kind of a data merchant on a way somehow to make sure that privacy concerns and PI and all these things are not taken care of. And then once you have this data, data mapping is quite a challenge. So data wrangling makes up for a lot of the time in this project. So you're dealing with missing data. You have gaps in the data which you have to decide how to handle those. You have missing time codes or varying channel names, and all these things are basically, this is before we attack the interesting part of the data. There's quite a lot of effort to be done in data mapping. And our goal in this project was to do some automatic data mapping. And on the right-hand side here, you can see how event data, so these service logs and error codes, are mapped automatically. You can see on the y-axis the turbine number. So it's a couple of turbines, and this is a stretch of a couple of years now. And you can see that everything that's green has been automatically mapped, and that's working fine. Everything that's yellow, so that green part is about 95% of the data. You have everything that's yellow that's automatically mapped, but there's some questions about it. So you have to manually check most of these things, and that looks quite a lot now. But what happens, for example, if you look at this part there, you may have a certain turbine status that is mapped here and that is carried forward just here. So we don't have to look at each individual day here or each individual time step. It's more or less check it at the beginning and see how that performs. And then there's some parts which are still manual mapping, and this is just because it's during that time period. It's maybe rare events, rare codes, which cannot be really automatically handled. So once we have this, we can apply different methods. And in our project, we used 6 or 7 different methods which we want to evaluate. And I'm just showing a couple of these. So one method is signal trending, where we basically take data for a single wind turbine or data for a wind farm, and we split the data into a training data set and an investigation data set. And basically from the training data set, we identify a reference state where the turbines or the wind farm is in normal operation. And then we use our signal trending methods to compare the current data to the signal trending data. And then depending on what quantity you're looking at, here you see an example for temperature. You can see, you can select some thresholds for your system when you want to have the operators, or when you want to provide a warning to the operators, or if you have an even higher threshold when you want to give out an alarm to the operators so they can immediately react. And you can do this on a single turbine level, but you can also do this on a wind farm level where you have these turbine numbers here again and time over here. So you can see, for example, one turbine here or 2 turbines which have a higher temperature than usual in this case, and you can identify turbines which have recurring issues. So that's one of the methods. Another one is the method for system identification. So basically, we are trying to estimate the turbine state from these high frequency data. Here you see on the left-hand side the active power in red and the wind speed in blue. So basically, that's the input for your power curve. And you can see that, of course, by the naked eye, you can see that there's some correlation here. And then we can use advanced statistical methods with stochastic differential equations to estimate the status of the turbine. And what we end up with is something like this. It's also the power here and the wind speed here. So it's the same actually as for the power curve. And in the center here, you have something like a fixed point of your system. So your system is basically, it's drifting towards here. And then you see where your current state is and how your system moves to the center line direction. And this is your equilibrium. And now you can compare, for example, the drift map at a different time and see if there's some issue here. And from this identification, we can then see, okay, there might be a problem. This has to be checked. And depending on who's your audience, basically, you can decide how to visualize that. If it's like a traffic light system, or you just want to give out an alarm, or whatever you want to do. This can be done on a single turbine level, but it can also be. It can also be on a farm level, of course. So you can compare different turbines here. And once you have these drift maps for different times and different states, you can check what the average of this wind farm or of this type of model is of this type of turbine. Then again, you can do something like a single comparison, like a single trending. Basically, what is my average state? Then you have a certain threshold here in the green area where you say, okay, this deviation from our average is still okay. You have an orange area down here where this is maybe a little bit concerning. And then you have your alert area up here, where your average deviates quite a lot from what you expect. And this is possible on the entire wind farm level as well. And also it's possible to not only include this very simple metrics using the active power and the wind speed, but also, as you see on the right-hand side, add multiple dimensions to that. Here you see the active power, the RPM, and the torque, for example, in a three-dimensional drift field. And of course, for the visualization, 3 dimensions is fine, but for the analytics, you can go even higher dimensions here. So once we have this, we want to connect this to our audience, basically to those using this data, and therefore we define some data products in this project, which can be different performance metrics, like tackling the performance of the farm, tackling different component status, or the overall status, or statistical evaluations, which turbines or which components are more troublesome than others. As the input, we have these several data sources, from the reports to SHM systems to MetOcean data, SCADA data, whatever. We feed these into our different methods. Not each method takes the same type of data, takes the same data quality. So that's something we are evaluating. What is the data demand for these methods? And once we run these methods, we get some results which we evaluate and basically compare the results between the methods. And then we come to this layer of a dashboard with the visualization. And in this dashboard, basically the users, depending on if you're part of the tech support here in the first, second, or third level, or on data science or management level, you can basically adapt your visualization upon your requirements for your decision making. So once we have this, as I mentioned in the very beginning, we have this soft and hardware platform where we have, on the one hand, historic data, and also we are working on getting live data input from certain wind farms now. And all these models will be implemented or are implemented in this software demonstrator. And you can see on the right-hand side, for example, this is just a mock-up of the dashboard. You can see, for example, in color code, the status of the turbine, and then you have 2 different representations here for the availability here. If that's what you like, that's fine. If that's what you like better, you can also have a different visualization here. And you can customize that, and it depends on what your application is, how many wind farms you have, for example, or how many wind turbines you have in your farm. You can add the geolocation for that. This is just Oldenburg house, so no wind farm in here. But you can have this, and this is part of what we're working on now. We're roughly halfway done with this project, and yeah. So in the end, this will not be a full software solution, of course. That's not what research is for, but we will try to get the practical evaluation by getting this demonstrator and making this the basis for some other extension. So this is the project consortium, basically our contributing authors. I'm just coordinating this project, so most of the work in this project is done by other people. And with this, I would like to thank you and be glad to answer your questions.
Hendrik, thank you very much. Are there questions in the room? That is Jake. So the microphone can be there. Jake.
Thank you very much. Yes, Jake Badger from DG Wind Energy. I found it a very interesting talk, so thanks. I was interested in first what MetOcean data was used, and then also if you could say something about how you kind of defined the reference, because it could be something about sort of anomaly compared to the other turbines, but then I imagine some turbines will be having different behavior depending on where their position in the layout and the wind direction and stability conditions and so on. So yeah, that was just interesting to hear a bit more about that. And then maybe if you could say something whether this work has led to any focus on what other sensors you would put in, or what data is sort of the most valuable. So a few questions there. You can decide.
Yeah,
Thanks.
Great. Thanks. That's great questions. Yeah. So MetOcean data is currently we're basically using the wind speed. That we have to focus on some of these issues, some of these components to investigate, and basically in the MetOcean part we are focusing on the wind speed right now, but we can also consider. So in the end, it's a question of what is available in a commercial wind farm, and you usually don't have stability measures. You usually don't have wave data. So that's why we are basically using the wind speed for this right now, but this can be extended. Then what was your second question?
The reference. The reference and the training period also maybe.
Yeah, so this is something we're doing manually now, because you have to find a reliable time for your where your turbines are operating well, and currently we're doing this basically on a single turbine case. But the point is we are very aware that there might be an issue once you compare front row turbines with some inner park turbines and use those as a reference. So now we define a healthy state for a single turbine and then compare it to itself. That was the third question.
Yeah, that was like whether it has created a wish list of what other data you would like to be able to add.
Actually, right now we are more or less overwhelmed by the data we have already. There's, of course, these MetOcean data. If you could have something about the shear, for example, or the wind veer or stability, that would be fine. But that's typically not available. And in terms of the turbine data, there is quite a lot of data. What's more crucial than what kind of data or which sensors? For us, it's more important to have these high frequency data, because oftentimes that's not safe, that's not stored. It's a little bit harder to get this.
Thank you very much. Thanks.
Thank you very much. Hendrik, also online there are some questions, but we are already a little bit over the period that we wanted to plan. So only 1 minute I will allow for the questions from Bose from Forwind. It's, how do you define the thresholds for the temperatures of the main bearings, for instance? And next question was, what methods would you suggest more? Your experiences works better when there is less data. So I think that you, for example, the 10-minute SCADA data. Can you shortly touch on that?
For the generator temperature, I'm sorry, I cannot answer that question, because that's simply this is some of my co-authors working on this, and I don't know how they exactly select this. I would assume that they are discussing this with the domain experts from our operators.
But if you could then connect them with to both Sumantra, and there's also from Xiaoli Yang is also a question on how to select the best method, and I think that will also require a lengthy answer. So if you could be so kind to connect them, that would be great. And then unfortunately we have to go to the next presentation, but thank you very much for your contribution today.